So that's that. All right. Now, so let's now think about how is information actually processed. Now, everybody agrees that we are in the digital age, right? So, how is information processed, right? And this is the first reading assignment I would like you guys to go through after the class. Again, that's basically from the chapter 1, all about number systems, and we will see why we need number systems. We need to re-examine number systems in a fresh perspective. Okay. Now, what I would like you guys to do is do a simple exercise. Okay. Now, examine your smartphone. You have a smartphone. I'm sure all of you must be having some kind of a smartphone, Android or Apple based. Now, and I would like you to think about what are the different things that the smartphone actually does. Okay. Take a minute or so and think about what you do with this on a daily basis. And let's see what you guys come up with. Okay. All right. So let me jot them down here. Smartphone. So these are some of the things that I would like you guys to think about, right? Sorry. Examine your smartphone and think about what do you use it for. Now remember that your smartphone is a device. It doesn't have life on its own, right? It's not like a living thing. It's a device, but it's actually very smart in terms of the different things that we can do with it, right? Now, and we have just seen that the computational power comes from these transistors and electronic circuits in a way that are basically fabricated on a silicon chip. So again, silicon chip is again dead matter. It's not like a living thing. So where does the ability to do all this functionality comes from in the first place? Have you ever thought about that? But before that, let's actually list out the different things that a smartphone does. Can you come up with the different things? Yeah, James.
I do a lot of messaging and also do a lot of processing on social media. So I do messaging.
Okay, social media. Yeah, that's one thing that most of us do. Yeah, Fletcher.
In more recent times now, it's being used as both a credit card and other forms of personal data storage, along with large scale photo storage in comparison to like previous generations of devices.
Data storage, absolutely. Kyle?
Yes, I also use my phone for voice recognition.
Voice recognition, okay. Yeah, Alberto.
I use my phone as my planner, actually.
Planner, very good. Yeah, Rodrigue.
I use my phone as a TV, and I don't own a TV at home.
Oh, okay. Okay. It's surprising, we have all of this list, but I still have to yet to hear somebody say I use it to make calls. That's interesting, right? What else?
Email.
Email? Yeah, you mentioned TV or videos, yeah, because you're watching videos. Rodrigue, yeah. Pictures. So yeah, so then this goes on. This basically goes on, right? You can really do a lot of things with these smart devices. You can do games, yeah. Yeah, you can weather track. So yeah, weather track. Okay. So yeah, the list just goes on and on. So that's why it's called smart in the first place, because it's a single device that can do all of these operations. You can listen to music. Yeah, GPS, absolutely. Music, MP3, right? We use that on that as well. Clock, yeah. Now, if I want to use a single word that would describe what we are doing for all of these things, what is the one thing that we are doing, or what is the one thing that your device deals with when it's doing all of that thing? Connect, okay. Data processing, right? It's basically processing data. Everything that we have seen, what we have listed down here, is basically data. As far as the device is concerned, it's all data for it. It's all data. So if I want to summarize everything, all the operations that the common thing that's common to all of these with regards to a smartphone, it's all data. It basically, a smartphone processes data. Okay. Now, again, going back to this question, right? Again, this reminds me of my own experience when I was a kid. Sometime, when I was a kid in high school, and I was very interested to actually. I was very intrigued by the calculator at that time. Calculator, it can, you punch in the numbers, it can calculate in seconds, and I was really interested in really what happens inside a calculator. Okay, and so I opened one, and I don't know how many of you have done it, and to my disappointment, I did not really see anything exciting. Right, all I found was a black blob there, and that's it. You have a keyboard, and then I was expecting to see a complicated mire of these wires going on here and there, and then you have these transistors, your resistors, and I was expecting to see a very complicated some kind of a circuit there, and I did not see that. It's actually basically a black blob. And so now I know what's really happening there. In fact, through this class, I'm hoping that you'll be able to actually make one, at least simulate one, a calculator. Okay. Now, so okay, the one I took apart was simple, just a regular calculator. That would have been very expensive, yeah. The one it was just a regular. It was not a scientific calculator. Okay. Yeah. So again, it goes back to the fact that as smart as they are still dead matter. Okay. So what we need to think about is, how are these devices capable of doing all of these operations in the first place? Okay. So let's look at this at a fundamental level. Let's talk about data in the first place. What do you think? Now, obviously, your device is able to do different things, right? You are able to, let's take some, just to make it, simple. Let's talk about sound. I'm able to play music on my system, on my smartphone. I'm able to play videos on my smartphone, right? I'm able to uh, text, write documents, and so on, right? Oh, so you can't read the. Okay, so let me do this. Okay, are you able to read it now?
No, it's far better. Thank you.
No worries. Okay. Rodrigue, do you have a question? I see that your hand is raised. Okay. So videos, text, sound. Let's just consider these three data forms, okay? And your smartphone is able to do that. Now, intuitively, again, this I would like to, in this class, I would like you to think intuitively, logically, okay, how things happen. Okay. Now, intuitively, what do you think? The data corresponding to sound, the data corresponding to videos, the data corresponding to text. How do you think are stored? Do you think the data corresponding to sound is something completely different or looks different than the data that is corresponding to, let's say, videos or data corresponding to text? What do you think? Or let me put it this way. Okay. So you have this device, which is processing all this information, sound, videos, and text. Okay. Now we know that we know definitely that our smart device is an electronic device. So somehow it is processing electronic signals, whether it's data or whatever else. It should be in the form of an electronic format, right? So the question is, the data corresponding to sound should be an electronic signal, video should be an electronic signal, text should be an electronic signal. But in terms of distinguishing all of these, do you think they are represented differently, or what do you think? Any comments from the class?
I think they'll be different because the data from the sound and video might be similar. They will come as a song or a video. Text message will come as a word or sentences.
Okay. Okay. Okay, James. So that's a good thinking. Yeah.
When I think about this, I think of waves, like sound waves, video waves, text waves. So I guess it depends on what type of sound. If it's acoustic sound, that might have a different way of being transmitted versus digital sound. So I guess digitally, I guess they will all be similar, like binary to ones and zeros, possibly.
Mm-hmm. And yeah, you're getting there. You're on the right path. So the answer is all of that information is, if you were to be presented with that information, there's no way to distinguish between them. As you mentioned, it's all zeros and ones. Okay, when I say zeros and ones, they are still. That's correct. There are, when I say zeros and ones, there are still voltages or currents. Okay, so you're still talking about electronic representation of these zeros and ones. Okay, now to get the analogy, consider our own human body, right? Now I'm able to hear sound, I'm able to see videos, right? I'm able to touch and feel something, right? Now, but inside, these are all electronic signals. Okay, so these are all, so when I'm seeing something, my eyes are the ones that are basically capturing the photons and converting them into electronic signals that are transmitted to my brain. Okay, so it's transmitted to the right portion of the brain, and my brain basically reconstruct the image. Okay, but at the end of the day, it's all electronic in nature. The signals that are being transmitted to the brain are electronic. It's basically being transmitted to the right portion of the brain. Likewise, when I'm touching something, I have some sensor receptors on my skin, right? And they would convert that pressure and the feeling to an electronic signal that is transmitted to the brain, right? Again, it's being transmitted to the right portion of the brain, so that it basically analyzes that signal and then then comes up with the sense of touch. Okay, so similarly here, data, if I were to see the data itself, you would not see that there is any difference in the data that corresponds to sound, the data that corresponds to videos, or the data that corresponds to text. Okay, so it's just that the peripherals matter. Okay, so when the data is being analyzed, data is being processed and sent to the right peripheral, for example, the speakers, that basically gets emitted as sound. When the data is being processed and sent to the screen, that's emitted, that's being manifested as as a moving image. But at the heart of data itself, the format itself is identical among all of these different data types. Okay. All right. So that's good. Now, yes, this is being recorded. That's correct. All right. So now what we will do is, let's actually take a simple example. And again, my goal here is to justify why we need to take a relook at the number systems instead of just directly jumping into that and getting on with it. I'd like to, provide some kind of a justification why we want to do that in the first place. Okay. So let's take the example of sound. All right. So why number systems? Why do we have to do this? Why do we need to look at different number systems? Okay, so I'm recording it on a different platform, so don't worry about it. You should be able to see it. So why number systems? Okay. So first, let's actually think at a very intuitive level. Okay. How sound gets propagated, how we actually make sense of sound. Okay. What we want to do now is, hypothetically, we want to create a device, okay, and electronic device, and we want to store a sound in it, sound as a signal in it, okay, or sound as a data in it, so that I can play that sound at a different time. Does it make sense? So we want to hypothetically create a device or think about a device that should be capable of storing, let's say, a song as a data within that device. Okay. Now let's look at the different steps that we need to take, what kind of components that we need to have to be able to do that in the first place. Okay. Now, so if I want to understand, if I want to do that really, I want to understand what is sound in the first place, right? What is sound? So let's go to the real basics, and then we'll build up that device.
Wave.
Sound is a wave. Okay. Is a wave. Sound is a signal, right? Basically, it's a signal. Anything that changes with time varying is called signal. Any physical parameter that changes with time is a signal. Sound is a wave. Okay. What kind of a wave is that? It's a pressure wave. Yes, it's a pressure wave. So what's really happening when I'm speaking, when I'm producing the sound, is that when I'm speaking, I'm disturbing the air molecules around me, right? And that pressure wave basically gets transmitted, right? And what happens then? It gets transmitted. So I have a pressure wave, the pressure variations in this air, in the air molecules that gets transmitted over the distance. And if you have some ear, let's say, you're hearing this. Let me see, how do you draw? Okay, here. Okay, and that's your brain. Yes. So you have some kind of an eardrum. You have an eardrum inside your ear, right? Let's say that's your eardrum. So your sound gets propagated as a wave. It interacts with the eardrum. The eardrum vibrates, and you have some very sensitive receptors, the vibration sensitive receptors in your ear that basically create this electrical pulses that goes to your brain, to the right portion of the brain, and your brain basically views that, or basically converts that into sound, right? Or a feeling of sound. Okay, so that's good. So we are able to do this. Now, if I want to do this, if I want to store, let's say, sound or a speech as a signal in a device. So let's say I'm trying to build this device, electronic device, and I want to store that sound as a data in my device. What is the first thing that I need to do? What is the first step that I should be doing so that I can actually get this? Any ideas? So somebody is speaking. I want to record that somehow and store it. What are the different steps? Now let's try to divide this process, this problem, into individual steps and see how do we actually get there. Going from the production of sound to be able to store that sound as a data in my device. Okay. So the first thing is I have this sound as a pressure wave difference, right? It's transmitted in the wave in air. I need to have some kind of a transducer. This is the transducer. So I want to generalize the term here. A transducer that would convert this mechanical wave that is being propagated in space into a signal, into an electronic signal. That's the very first step I need to be doing, right? The first step I need to be doing is catch those sound waves and to convert them into a signal, into an electronic signal or an electrical signal. How do I do this? I use some kind of a transducer that would convert the mechanical energy to an electronic energy, electrical signal. And somebody mentioned microphone. I can do that. So I can use the microphone. What does the microphone do? So you have, again, similar to your ear, you have some kind of a vibrating membrane there that basically vibrates and converts that vibrations into a signal. Okay. So that's the signal. Now I have a signal. So instead of talking about sound in terms of a pressure wave, now I can talk about sound in terms of a signal that's varying with time. A signal that is electronic in nature now with time. So my sound signal can now look something like this over time. That's your time. That's your voltage axis. So your transducer has converted the pressure wave into a voltage. So that's the first step. Okay, get a microphone to record the wave. Okay, so I don't know how to record it yet. At this time, I've converted that into signal. Now, let's say I have this signal. Let's say I have between time t equal to 0 and time for, let's say I've recorded it for 10 seconds. Okay, and I want to store that 10-second clip in my device. All right, as an electronic signal. All right. Now, how do I do this? Why would I need to do it? Why do I need to turn it into a digital signal? What is a digital signal in the first place? Right. No. It's digital signal. Yes, ultimately we'll be doing that. Ultimately, we are going to go there, but we need to do it in steps. Okay, sample the voltage just generated. Why do we need to do that? Sample. You're right. We need to sample it because if you think about this, even a segment between 0 to 10 seconds, a continuously varying signal. Okay. How many points would you have there? If I want to store all this signal in a device, what are you working with? Infinite, right? Because I will be having infinite number of points because I have a continuously varying signal, right? I have an infinitely varying points because between any 2 points I take, I have a data value because it's a continuous signal. So from continuous signal, which we call analog, I would like to discretize it. Discretize it by sampling it. Sampling it. Why do I need to sample it? Again, I need to sample it because now I can work with a finite number of samples. A finite number of samples. Otherwise, I will be working with infinite number of samples, and you will be needing infinite amount of memory to store even a short segment of 10-second duration. Okay. Sampling. I have to sample it. What do I mean by sampling? Again, for the non-electrical majors, yeah. What it means is, instead of taking all the points and trying to store all the points, I would just take few points spaced apart. Okay. So I will take point here. So I will sample it at a frequency so that I don't lose the content of the signal itself. What it means to say is, if I take one point here, let's say, and another point here, that's not a right way to sample it, right? Because between these 2 points, I have all of these variations in my signal, which I'm basically, if I'm doing that, I'm going to lose all that content, the signal content in my signal, right? So obviously, this is not the right sampling. So there is a principle by which we have to sample. So that is called the Nyquist criteria. So you need to sample it at a high enough frequency, so you don't lose the signal quantity or the signal. You don't lose the signal content. Okay. The Nyquist criteria, which states that you need to, if I know the bandwidth of the signal, okay, then I need to sample that at least twice the bandwidth of that signal. Okay. So that's the twice the bandwidth of the signal. So now I have to sample it at least twice so that I don't lose the signal quantity, signal content. So now, instead of working with infinite number of data points, now after sampling it, now I'm working with finite number of data points, and so on. Okay. All right. So that's called discretization step. All right. And these are voltages. Okay. Now you can think about, if I want to store this as an electronic signal, right? That means that basically, points you to storing these values. So if I'm able to somehow create a device with these nodes on it, these are voltage nodes that can be adjusted to any voltage value. Okay, these are the voltage nodes, let's say. Then I can adjust the voltage value at this node to correspond to this first sample. Because this is the sample 1, 2, 3, 4, and so on. Okay. So in other words, I would measure the voltage here. Let's say that these are lying between 0 and 5 volts. Let's say this is 5 volts, that's 0 volts. So you know what this voltage would be. Let's say that's 1.125 volts. One idea is I would create a device with these nodes that are present in the device, and I would somehow come up with a scheme to adjust the voltage of these nodes to these sample values. So I will adjust the voltage of this node to be 1.125 volts. That corresponds to this sample. Let's say that is 1.3 volts. That's 1.45 volts, and so on. So each of these voltage values on these nodes corresponds to these sampled values. So now I have a device where I'm able to store this sound clip as voltages along these nodes. That's one intuitive way of thinking about how do we actually get data to be stored. Okay. Does it make sense? Are you with me until this point?
Yes.
Okay. So very good. Now it turns out that it's not trivial coming up with such a scheme. Okay. Now as you can already see, this particular sample, this value may be 1.125. This is 1.3. The variations are infinite, right? The variations in the different sample values I may have are going to be infinite, right? Because this could be 1.1, this particular sample could be 1.1275. So that the number of variations are going to be infinite. So the next step I have to do to reduce the number of variations is to what is called the quantize the signal. So now we have sampled the signal, that is the discretizing along the x-axis, that's the x-axis. By quantization, what it means is I'm also making these different levels along the y-axis, so that now I'm working with finite number of levels. The sampling on the x-axis gave us finite number of samples. Quantization on the y-axis gives me finite number of levels I can work with. So my each node value would be within a range of quantized levels. I hope that makes sense. Okay. All right. So this is what I mean by that. So the next step is called the quantization. So basically I'm dividing my y-axis to different levels, and now we will talk in terms of levels. Instead of actual voltages, I will talk in terms of levels. So this is 0, 1, 2, 3, and so on. So now, instead of actual voltages, of course, each level corresponds to a voltage, but I can simply talk in terms of levels. Let's say this particular, the first sample, again, I will come up with a rule so that if it's closest to the top level, then I will basically take that as a level. So let's say that's level 2. So instead of this, I will basically say that's level 2. So whatever voltage that is associated with level 2, and you can easily calculate, right? Depending on the number of levels, let's say I have 100 levels between 0 and 5 volts. That means my each level would be 0.05 volts, right? So that will be level 2. And again, I will start writing in terms of level, describing each node voltages in terms of a finite number of levels, instead of working with infinite number of levels. Okay. Now again, but at the electronic signal level, it's still being able to adjust to that level voltage. Okay. All right. And it turns out that that's also not trivial, right? Because you don't, if you want to do this on a very large scale, I don't have an easy means to adjust the voltages of each node to this continuously varying voltages of the levels. Okay, and that brings us to alternate techniques, and this is what we will continue in the next class. What can we do about this? How do we solve this problem? Okay, so that I can actually have a device that can actually be realized in principle, that can be mass produced, and so on. Okay. All right. So with that, let's conclude this class today, and make sure you go over the first chapter of the textbook, and I'll see you guys on Tuesday. You have a good break. All right. Thank you, guys.
Thank you.